Hello, and welcome to the Energy Resilience Lab. Our lab is dedicated to giving you the knowledge, skills, and the encouragement that you need to become resilient and to get on the journey to energy independence. Our shows are broken up into 4 different formats. The first one is informational, so that's where we'll be training you on different systems and giving you more information on how systems work. The second one is interview style, where we'll be asking questions of someone that's very knowledgeable on the subject that will share with you what they have learned over the years, and they'll give you more insight into what is going on in the world around us with regards to energy and power. The third is news related, so that's where we will share breaking news and new developments in the market, in the energy storage market, different products becoming available, and different technologies becoming commercialized and getting to scale where the average consumer can take advantage of those. And then the fourth is question and answer. So that's where we will answer your questions. So if you put questions in our comment section under the videos, we will go through all of those and read them and then report on those and answer your questions going forward. Just to get started today, I would like to go over different forms of solar and the different reasons why you might want to use different types. So 10-15 years ago, almost everyone was using string inverters, and what that is a system that had high voltage DC solar. So when you have a solar panel, I guess we could start at the solar panels themselves. So there's solar cells in each panel, and each one provides a little bit of voltage and a significant amount of current, depending on the size of the silicon wafers. So you make a solar cell, it has a specific size, and that size will be proportional to the amount of current that it provides. So a solar cell is actually a current device, not a voltage device. So when the photons from the sun hit the solar cell, they displace electrons in the silicon wafer. So what that does is it drives a current through the solar cell itself. So it is trying to push electrons. And so with that, you're going to have different physical attributes of depending on your size, you're going to get a different current. And then just with the type of solar cell, you're going to get a certain amount of potential or voltage. Usually in the case of a solar cell, you're only getting under power around 0.5 volt per cell. So when you put all the cells together, you string them to have enough cells in series to get a voltage that's usable for your system. So there's a lot of systems out there, like talking about the small compact energy storage systems that run on 12 volts, and each one of the solar panels that you make has to have enough solar cells in series to be able to charge or push current into the battery. So that's kind of the physics of how a solar cell and a solar panel works. Different types of electronics that you can have on your system would be just a PWM charge controller, which is just pulse width modulation. So we talked about duty cycle a little bit in the power segment that we did. And so a pulse width modulated solar charge controller just allows the current through for a short amount of time and then turns off. So if you're looking at pulse width modulated solar charge controllers, they are just switching, and that can regulate how much current and voltage is getting to your system. And it will control how much power is coming from solar and kind of try to maximize that the best it can. The next level up would be a maximum power point tracker. So in power systems, you're going to have internal resistances of both sides of the system. And so essentially with an MPP charge controller, it will look at the battery's internal resistance and the solar array's internal resistance and maximize their potentials for energy transmission. So it will take in the solar at whatever voltage and current that it needs to maximize the power that you're getting from that system. So given all of the environmental conditions, temperature, the weather condition, if it's rainy, if there's water on the panel, if the sun is hitting it directly or if it's overcast or hazy, that's going to change the amount of electrons that are getting displaced in the solar panel. So that's all to say that if you get a more smarter charge controller like an MPPT, it's going to keep modulating and changing the amount of power it's taking from the solar panel to get the maximum. So it will take a little more current or a little less current, and then it's kind of guessing and checking to see which direction is going to give more power, and then it will follow that direction, and it will just continuously vary to maximize the power that's coming from the solar panel. These types of systems are now becoming a lot more ubiquitous, so like even the small energy storage devices have MPPTs or some sort of power transmission maximizing device for the solar, just to get as much as you can. Next, so that's kind of in the small scale and with the small panels. Once you go into a larger scale, it is essentially the same thing, but you need to stack more panels in series. And so going to the home systems, like I was saying, 10 or 15 years ago, they started doing string inverters. And string inverters are inverters that have a high voltage DC input, and then they have an inverter that syncs with the grid, and it will maximize the amount of power it's getting from the solar, and it will export the maximum amount of power to the grid in AC form. So the problems with that is that, so back at that time, a lot of people wanted to be more resilient, and with a string inverter there is no resilience essentially added to your power system. It's really just a play on getting the energy, creating it, and exporting it to the utility. So you're essentially just trading energy. So you send them a kilowatt hour, and for every kilowatt hour you give them, they will give you one back. And so you just send a ton of power during the day, and then at night they will allow you to use your credits. So that's where you get to kind of a net zero situation. So a net zero situation is where you're exporting so much power, either at a 1-to-1 or at a different ratio, and your credits are more than you need to use throughout the year. So it's kind of like a energy laundering system. So you're taking energy, exporting it sometime, anytime that it's available, which is not always optimal for the power company, but they will do it just because it's a very small amount of power that's being generated by solar. So just for an idea, here in the area where I am in the Intermountain region, one of the power companies has less than 1% of their energy production from solar. And so it's a very small amount, so it doesn't really hurt to add solar. So it's just one of those things that they can add that can help us feel better about our energy production and our carbon footprint here as we're living. But it is kind of a laundering thing where you're just exporting the power and then getting power later. And so you're kind of trading clean power for the dirty power through the night when you need it. It's not optimal. It is good. It does save you money. It can make you energy independent, and that's one of the goals here on the Energy Resilience Lab. So that does fulfill the energy independence portion. Moving forward with this, so there was those string inverters, so you have high voltage DC solar coming to the inverter. The inverter is connected to the grid, so it will sit on the grid and watch the grid and just push the power to the AC grid as it comes from solar. Later on in the probably 8 to 10 years ago, they started making micro inverters, and that's where, again, you're just taking your solar, maximizing the amount of power that you're getting from the solar, and injecting it into the grid. In this case, you're just taking your 30 to 70 volt home solar panel that's on your roof, and you're putting a small, very small inverter, a micro inverter, on each panel. So now you're buying, an array of maybe 20 to 30 large 300 watt solar panels, and then you place an inverter on the back of each one. And so now what that does is that it does break out all of the power. So each solar panel just produces whatever power it can, and it can export it onto the grid. Kind of the drawback of doing a string inverter that cause them to go to microinverters is that if you have solar cells in series to get a high enough voltage for the string inverters, the current through those solar panels needs to be the same. So in a series circuit, the current is always the same. In a parallel circuit, the voltage is the same. So the current has to be the same through the solar panels. And some things that can stop solar panels from producing the current would be if the solar panel is dirty. So you'll have they can get dirty from different animals, like birds will add nests to your solar array, and you get dirt and dust and silt. Everything from the environment blows onto your panels, and so if there's one panel in particular that's more covered up, it induces resistance in your system, and so that limits the amount of current that can go through that string. So that is something that derates all of the panels in that string. So you may have 30 panels and 10 of them on each string, and a string is just a series of panels that are connected in series, stacking the voltage to the high voltage. So in one of them, if you had one dirty panel, it's going to reduce the current on all of those panels, and so you could lose a third of your solar array's production because they're getting dirty. But to fix that, you can just clean your solar panels, or there's new things that they're using, that they've started using, which would be a DC optimizer. And what a DC optimizer does is it takes the power from your solar panels. So you have 10 solar panels, maybe one is underproducing. The DC optimizer will take whatever it's getting from the solar panel and convert it into the power that is going to maximize the current. And so if you have a solar array of 10 solar panels and one of them is producing a tenth of the power of the rest, that one DC optimizer will adjust the voltage and increase the current coming from that panel to make it so that the current can be maximized across the whole string of solar panels. And in doing so, that makes it so you're back to kind of the AC, like the microinverter division of power. So when you have the microinverter, each solar panel just provides what it can and exports. In this case, with the DC optimizer, it's doing the same thing, but it's just in a string. So that's running to a string inverter, was kind of the old way to do it. So we've got string inverters, microinverters, and then DC optimized strings of solar. And then now in the market, there are different systems that you can get that add resilience to your home. So to get resilience, you really have to get a battery operated system. And just from an architecture standpoint, it is nice to stay DC between the solar and the battery and not have to do the conversion to AC. So the drawback of doing an AC coupled solar panel is that it is converting to AC immediately and exporting. And so that's going to lead the ROI to be maximized if you just export that power. Because if you want to keep it on site, you are transforming it from DC to AC on the roof, and then in your home you need to transform it again back from AC to DC to get into the battery. And so you can skip some transformations and some losses if you take in high voltage solar from the solar and then go into your battery just through one DC to DC system. So with kind of these newer systems that you can get now with batteries or without batteries, they'll take in the high voltage solar, and then the battery will be able to capture that energy. So what that allows us to do is it kind of takes away the requirement to need to do net metering, which is where you're exporting power to the power company and they're giving you a credit. You can negate all of that and just do a solar energy storage system that will take the solar that you're receiving from your solar panels, take that solar energy, and it will put it into the battery. So now you're still producing a lot of power during the day, but you're taking the power and splitting it, just covering the loads that you've got during the day, so the utility company doesn't see that you're using any power. So you're producing the exact amount of power that you're using throughout the day, and then any excess goes into your battery system. And then the third level, if it gets tapped out, if you don't have enough energy storage, then you could allow the inverter to export and get you some credits if you have the net metering agreement. So in this case, you can actually use all of your renewable energy. So you're using everything on site. It's generated on site, stored on site, used on site. And this is the ultimate in resilience and in energy independence, because you have all of the systems in your possession to give yourself all of the power that you need to run the systems that you want. So in the event of a power outage, your system is still there, and you can use it independent of the grid. Let the grid go down. The inverter, with all of its safety and logic, will isolate the grid so that it's not exporting power to a grid that's down, because that can cause problems for the linemen that are working on those lines. Because if you inject power into a grid that's down, you become the generation source, and it will cause the linemen it could cause them to get electrocuted. They are wearing all of their safety equipment because there can be inadvertent connections of generation. It could be a generator that isn't isolating from the grid, or solar inverter, and that can cause dangerous conditions for them. So this is all to say that AC coupled systems are great. They can make you energy independent, and that if that is your goal to become energy independent, then doing an AC coupled system that just converts the solar directly to AC and exports it immediately, that is probably the best solution. It's getting harder and harder to do that because the power companies would prefer that you just take care of yourself and move the power and use it throughout the day, so they don't have to take your power during the day and then give you power at a different time. Just as an anecdote, these systems, I guess, in California, they've mandated that everyone have solar, essentially. So every building has to have a certain amount of solar, and now they've mandated that it has to have a battery as well. But just to give you an idea, they were producing in the middle of the day, just from their solar for the last few years, maybe 5 years or so, their solar production produces more than they use during the middle of the day. And so what that causes is your solar production actually makes it so that the usage for your power plant goes negative. So your power plants need to stay on, because if a cloud comes over, right, the power drops out, because solar isn't consistent. It only is created when there is sun. But so that's a concern. You have to run your power plant to take up any issues that the solar has or the wind has. So if the wind and solar is overproducing and you actually have more power than you need, you have to sell that power or give it away to neighboring regions. In the case of a utility, California can give power to the Intermountain region or down to the Arizona region, and that's what they've done. So they've actually paid in some cases to give the energy away to these regions, just so their system can be more stable. But that's what we're trying to avoid. So the normal power usage for a home, if you average it across everyone, essentially is going to have a power peak kind of in the morning. Everyone's cooking breakfast, getting ready, doing everything they need to get ready for the day. And then it'll slow down, and then all of the loads for business will come up during the day. And then in the evening is really when the highest peak usually is. So if you have a solar array, it's going to produce from 9 in the morning till 4 or 5 p.m., depending on your time zone and everything. But that's when it produces power. So you're going to be exporting 10 kilowatt of power or whatever, which may be 5 times what you're using. So all that extra power is going and helping with other loads in your area. But what that does is the solar falls off, and then everyone gets home and starts cooking and doing everything they need to for their families. And that causes a new spike that's even higher in the evening. And so as these power differences get higher and higher, it makes it more and more costly for the power company, because they need to be able to manage that peak power. So they have to keep the power plants online sufficient that they can cover all of that peak load, even if the load is going negative in the case of California or other regions like that. So for us, if you're doing AC coupled, it's just you're exporting power during the day, covering loads for other people, which is great. That still is reducing the carbon footprint for the whole region, and it is making you energy independent because your power bill will be zero or close to zero. But if you do take care of yourself and get an energy storage system, you can become resilient. So that means power goes out, you can still use the solar, you can still generate, and you can get through the storms or whatever's going on, or the problems that are going on with the utility. And just in general, it's going to be, just to give you guys kind of a synopsis of this episode, you have the string inverters, they're just going to export during the day. You have the microinverters, they export during the day. Or you have high voltage DC inverters that also have a battery coupled to them, and those are going to make it so you can be energy independent and resilient at the highest level. So you can get as many batteries as you need, inverters as you need, and make a system that will keep you essentially, like, it's not even net zero, it just is self-consumption. So you only consume all of the energy that you're generating on site. So then your carbon footprint is truly reduced for the total amount of energy that you can accumulate from your solar array. So AC coupled systems are great, they're useful, and they are a valuable generation option for different countries and utilities. They aren't consistent enough to cover the base loads, so we do have to manage that. So the most optimum solution would be to have solar with a battery, in most cases DC coupled. There are systems that are AC coupled and also have batteries, and they will communicate and charge off of the microinverters. They will charge their battery, and then they will back up your home or your critical loads panel. But kind of the concerns I see with that is you're purchasing another inverter. So you've already bought 10 kilowatt of microinverters, and then you're going to buy another inverter that's 8 or 10 kilowatt to convert the energy and put it into the battery. And so to make the most concise system, just combining it so that the high voltage DC solar can get to your inverter, and you can DC optimize those solar panels to maximize the output even when there's inconsistencies in a string of panels. That's going to be your most optimal option to make a resilient system. The other things I've noticed just in the field, kind of anecdotally, is that with AC coupled systems, the inverter, your main inverter that is adding resilience to your home that would have the battery coupled to it, has to provide the voltage for your home. So it's creating the voltage that is powering your home. And the AC coupled inverters, on like the microinverters or string inverter, is pushing onto the lines more voltage, and then the main inverter has to draw that power off. So it's creating the voltage and charging itself from the AC coupled inverters continuously. And there are some systems that I've seen that work pretty well, but there can be some flashing associated with the just interaction of the inverters. So both of the inverters are working together to make the power potential on your home sockets, and in some cases when it's drawing, if there's always going to be inconsistencies in the power from solar, and so the main inverter has to draw power and discharge power in the millisecond kind of range. So every 3 milliseconds it needs to adjust how much power it's taking or giving to the system, and that's mid-wave. So it's about 20 milliseconds per sinusoidal full wave, and within that wave it has to adjust the power that it is drawing from the AC coupled inverters or that it is providing from its battery to standardize that voltage and to make it operate. And so some systems that are lower frequency in checking and adjusting the power you'll see the voltage go up and down within the wave, and that can cause like LED lights to flash or other systems in your house to be disturbed by the power because it's not perfectly consistent. So those are the things I've seen in the field. If you guys have any comments or questions, please add them in the comments so I can see what you guys are thinking and what you guys are working on. Please add any questions you have with regards to making an AC coupled system or a DC coupled battery energy storage system, and we'll answer your questions. Thank you guys. Please like and subscribe to these videos. We're trying to get the word out, get people more interested, and to help them become energy independent and more resilient in their homes so they can take care of themselves. Thank you guys, and have a great day. Goodbye.